So one of the things that I hate is that Rust has this perception of being very hard to learn. And my hope is we can fix that for you. I'm now pretty happy. So we are at chapter 1. But I want to take everyone to chapter 3. And the other thing I'm going to bring up is the playground. So Rust is a compiled language, but thankfully we're able to actually get things run relatively interactively. Now, one of the things that's kind of annoying about Rust is that sometimes you can reuse variables, but sometimes you can't. So I'm going to create just a structure, and it's going to have not much in it. So we'll have like one field. It can just be a. What should it have? It should maybe have a usize, which is an unsigned integer of the size of a pointer. If that, I'll just call it n to confuse. And to create that, I got d equals demo. I need to add a little bit of. Well, let's see if we can figure this out. So I'm going to try and print this thing out, demo variable. What I'm hoping that to trigger is, oh, I got myself confused there. What I'm hoping to trigger is, firstly, oh, we have a problem that we can't actually print it to the screen. Before we're able to do that, we need to derive a trait. I'm going to park the term trait for now, and we'll describe what that means very, very shortly. Basically, a trait is an abstract class or an interface with a funny name. Hopefully that makes sense to everyone else. So we need to implement a trait. Now there are two. One is debug, the other is display. You'll see here that it's asking for display. But in this print line thing, we need to use weird syntax. I'm just going to get rid of the string from Rust. We're just dealing with this demo variable. I've got this derive step, which asks the compiler to automatically implement the debug trait on our behalf. Now, the print line macro, and macros are kind of sort of functions, requires a little bit of extra syntax to make use of the debug trait. Okay, so now we have our demo in is 42 right there. Now, what happens if we try and use demo twice? This probably might work. How do we go and create a problem for the compiler? What you're going to run into at times is a block. I'll just check the chat because there might be questions where we already are. Oh, whoa, there's heaps. Having trouble seeing the top. There we go. Okay, good job. Doesn't sound like we've got any direct question. That's useful. What we're trying to do is induce a lifetime problem. Has anyone encountered that before? Font is a bit small. See if I can increase the size of this thing. Bang, bang, bang. I'll get rid of this banner since I assume that everyone can already see where we are. Lots, I've encountered it lots. Cool. So I'm going to go back to the live book. And I'm going to try and find, oh, that's all of the books. I want my chapters. Where are they? Table of contents. From introducing Rust to lifetimes, ownership, and borrowed. So this is one of the areas that people most commonly say that Rust sort of sucks. They introduced this language that no one else does, and it's complicated, it's difficult to learn. So what I would like to emphasize is that you will learn it. And it's really important to give yourself permission to take the time to figure this all out. It might help by starting with the rationale. The lifetimes metaphor enables you to write concurrent programs without worrying that different parts of the program will call each other. And so if you go through chapter 4, we're setting up something that's very similar to what I've done in the playground. This CubeSat variable structure is very similar to the demo one. We've got a different type of integer. And we've got a usize in this side, whereas back in the chapter I've got a U64. That's not super relevant right now. But what I want to create is a problem like this. The compiler is saying that you're not allowed to use something twice. So maybe one of the things that I will do is put it in a function. And I'm going to remove the output and bring the print line statement into the function itself. And this one is going to, so we had demo, we've now got a satellite, a tiny little one. And print line is going to be in here. I'll just call this our tiny little cube satellite. Before this, when this chapter was written, Starlink and Elon Musk's stuff hadn't been invented yet. Okay, so I've got a structure defined, a function defined. The function is going to do exactly what we had before. Which is just printing out the value using the debug syntax. And before, we were able to print out our CubeSat twice. This time, I expect that the same behavior is actually going to cause a compiler error. Oh, there we go. We just broke our compiler. So how do we fix it? Actually, I'll just stop there and allow people to ask any questions. The reason why I'm spending some time on it is that this feels like the kind of thing that new programmers to Rust are really confused by. The first thing, and this is going to sort of sound counterintuitive right away, is that we can actually change what we accept. Oh, did you mean? Yeah. I thought that oh, that's not what I wanted to. I can't confirm. I love that. I sympathize with you completely. Okay, so what did I do there? The first thing, our first definition, our satellite variable, and I would spell it in full, but my spelling is terrible. And that's a good question, Playguru85. I will get back to you. Okay, so right now we've got set, which is asking for a CubeSat. When I add the ampersand, it changes to asking for a reference to CubeSat. And Rust has two types of references. It has read-only references and read-write references. This mut, it sort of, what suffix is a good word, to ampersand, will change the type of reference to a read-write reference. Right now though, we don't need to change any things inside CubeSat. So we don't need what's called a mutable reference. I like to call it a read-write reference because the language is a little bit simpler. Yeah. So when we run this, it'll be happy. Now, why did just changing what the function accepted to a reference enable the compiler to be happy? Let me take you back to where we were. When I don't take a reference, I ask the compiler to give ownership of this variable, or actually this value, to the check status function. But that doesn't return anything. The responsibility of the owner is to destroy any objects that it owns when it comes out of scope. So what this does implicitly is call a thing called drop. And this extra function call is added by the compiler itself. When there's a reference, the ownership is actually retained by main. This tiny on line 12 is the actual value. And when it is used in lines 14 and 15, we then have this situation where the owner is the main function. And then drop will be called here. I'll pause that to allow people to chew on that. I've got to answer this question about whether this is true for all variables or just complex one like the struct. And it's a really good question because unfortunately for new programmers, the behavior is different for primitive types to complex types. I'm just going to quickly add a very small function, which is check primitive status. And this will be a usize, because we have already encountered one of those before. Now you'll apologize for my syntax. Just as an aside, I try to avoid idiomatic Rust in the book, intentionally, because I want the book to be accessible to people who have never programmed in Rust before. You shouldn't need to learn the language, all of its idioms, and all of its everything just to read the book. There's plenty of time to learn idiomatic Rust after you've learned the basics. Now, I'll just, so I've got this check primitive status, and I'm just going to create a new variable with the let command, well, keyword. It can be 50 because I've already used 42. And now notice I'm not going to use the reference syntax. And up here we don't take a reference. So we have a different warning that we've compiled a function that we never use. But that's not the same thing as what we were worried about. Now, for me as someone who learnt Rust, trying to figure out when I need a reference, when I don't need a reference, was super confusing. I'm hopeful, though, that I can explain why. So we talked very early on that the trait system is what defines behavior in Rust. Traits are the core. Now, if you have implemented a special trait called copy, then we can opt in to different behavior. Sorry. The nervousness is definitely getting to me. And I'm going to take away the reference syntax. By the way, if you've got any questions, just add them to the chat. More than happy to answer anything. Welcome. We've got like 40 people watching now. That's pretty cool. Oh, so, but to get get copy, I also need to implement clone. So how does one implement clone? Well, very, very simple structures that only have primitive types. Oh, that's a great... There's two really good questions. I'll get to this very soon. If you've only got primitive types, you can derive clone and copy, because all of the primitive types themselves implement clone and copy. Now, I've got a bit of mess that I'll clean up, and then I'll get to answering the questions. Okay, so are primitives always on the stack? If you don't know what the stack is, you're still welcome here. I just want to back up and just explain what the stack is for anyone that doesn't. I would very much encourage you to read chapter 5, because it explains exactly what the stack and the heap are. And I've had one person, I don't mean to segue too far away, say that this is the nicest technical writing that they've ever seen. I'm not going to go find the tweet, but I will maybe later. Okay, is usize preferable to something like, sorry, first answer the question about primitives. So are they always on the stack? Yes, they are. Everything is on the stack unless we add a pointer. Now, if you don't know what a pointer is, again, you will if you read the book. If you haven't got the book, that's fine. It's really cheap. And I think Candace has got an offer, so scroll up in the chat. And so we need a box. And that's a function, not a... Now a box is just another metaphor that's kind of poorly described. But this syntax here, for people that know what the stack and the heap are, will allocate 42 on the heap and have a pointer to that 42 on the stack. Now, Rust is very what we call stack heavy. So everything local, unless it's a reference, is allocated on the stack. That means that Rust is very good for embedded programming because you don't need dynamic memory allocation. Now, next question. Is USide preferable to something like i8 all the way through i64? Maybe. So, if you know what data you're dealing with, you may wish to only give yourself 16 bits. But commonly, you want to use your CPU's native pointer type. Now, again, if you don't know what a pointer is, or you don't know what a CPU architecture is, that's all fine. If you have been programming Java, everything is this type, i32. So, and if you're trying to understand what all of these different integer types are, I believe that I've explained them somewhere. Where have I explained them? So we talk a lot about different integer types, why we might need it, we have unsigned integers versus signed integers, but I'm getting a bit lost in the dark now, so I'm just going to maybe stick with my lifetime store. Last question. Okay, is it preferable to use? Why is that also iSize? That's a good question. So, iSize allows you to represent negative numbers. A usize does not. The iSize type has a sign bit. And when that's flagged, we're talking about a negative number. And when it's not, we're talking about a positive number. What that allows us to do? Yeah, so it's, represent negative numbers. So, so let me put that in practice. So I've got this tiny little structure. That tiny is CubeStat. And we've got an i32. There's a whole family of integer types in Rust. Don't worry about it. You will learn to love it. So yeah, hey, look, fantastic. We are able to represent negative 42. Now if we change the type to U32, this is going to blow up on us. It's going to say, hey, sir, I don't think that you know what you're talking about. So politely, it's going to say that unsigned values cannot be negated. Now, if you are like a speaker of English as a second language, this is a complex way of saying it can't this type cannot represent negative numbers. So if you are storing count data, this is perfect. And the reason why I'd use an unsigned integer type is that you get double the amount of numbers that you're able to represent inside the same number of bits. Because you don't need a sign flag, you've got one extra bit. And the way that binary works is every extra bit doubles the number of numbers you can represent. Why do we need eye size? I'm not. Oh, yeah. I'll allow other people in the chat to voice their opinions about why we need eye size as well as U size. So U sizes clearly correspond to like the pointer width, but that isn't so clear with signed integers. And we'll see if anyone is able to answer that question. Otherwise, I can have a go, but I'm kind of driving forward on this lifetime problem. So again, for anyone that's new, we're playing around in the Lightbook, and we are focusing actually on section 4.5, which is resolving life ownership. We talked a little bit about why they why they occur, and we're going to be talking about 3 strategies for getting rid of them. The first one we've already talked about was to use references. And the next one is, so this just explains that we can have a mutable reference as well as a read-only reference. Now, one of the other things that we can do is, it's more of a software engineering problem using fewer long-lived variables. I'll just duplicate the value. So there are 2 traits that I want to talk about. We've actually touched on them both. One of them is copy and the other is clone. In order to be copy, a type must be clone. So clone comes first. So up here, we've implemented both. But allow me to show you what happens if you've only got access to clone. This could occur when you have complex types. Instead of the copying of the behavior happening by itself, you need to explicitly call clone. Oh, I've still got the wrong type in there. Okay, so it's actually still not happy with us. It's saying that the second access is not valid, which makes sense because by the time we reach line 17, it's already been deleted. We've already called drop implicitly. So we need to clone it first. And then the clone will be sent to the first call of check status, and the original value will live on. So what's being printed here isn't the original value. It's being copied twice, once in 16 and once 17. And the original value, to find line 14, is still available for us. So we could do whatever we wanted. One of the things we might want to do is change 42 to another value. So how do we do that in Rust? First thing we need to do is change the variable to be a mutable value. Mutable, again, if you're new to if you're new to English, just means changeable. A mutable value can have its internals changed. Okay, so that's easy. But what if you can't just implement, just derive? Oh no, actually that's describing derive. Oh, here we go. So if you need to do it manually, here are some tricks. I'm going to use another feature of the livebook, which is being able to copy and paste automatically. I'm just going to copy all of that in there. And let's describe what's happening. First of all, this syntax kind of looks somewhat kind of, what's a negative word? It just kind of looks absurd. There's nothing happening in here. We're saying implementing, which is what this is shorthand for, these quote impl blocks is the way that Rust programmers tend to refer to them. But there's nothing implemented in here. And that is because they're just what we call a marker trait. So copy is an indication to the compiler. It's not a public interface in the same sense that you might be used to it. There are several marker traits, and they provide a guard for sort of a syntax at a compiler level. I don't know if that makes any sense. Hopefully it does. I can explain that if anyone's unsure. Just feel free to, again, ask it in the chat. Okay, so to implement clone, and in fact, to implement any trait, all I need to do is implement its methods. So clone has a single method, and we can find the definition of clone on the Rust doc site. So if I Rust standard we're looking for clone, aren't we? When are we going to have the printed book of about 3 years ago, hopefully? I believe that we have some printer delays, or actually there's still some stuff that I've got to fix. I think the timeline for the publication is September these days, but I'm very hopeful that we'll come faster than that. Just in case you're curious about what I've got to fix, people have been very kindly commenting on the book as it's been developed. And there are questions that I have tried to answer as we've been going. And there's one that I still should probably get to. It was added a year ago, and 7 people have updated it. I've added an acknowledgement, I think. I might do that again. So thanks. I'll say I will get this fixed. There's about 300 of these that I've got to fix. So let's talk about clone. So if I find a trait and I want to know how to implement it, first thing to do is go to the doc site inside Rustlang. Now it says the required methods. The term methods is a little bit confusing here because Rust doesn't describe itself as an object-oriented programming language. the reason why we use the the name method is that they look like methods when we use them. So we've got tiny.clone. Now, this is the only thing we need to do to opt into clone. We just need to return we take a reference to ourself, and we need to return a type of ourselves. Now, the syntax for creating a new type is with a literal. Now, I've just realized that I actually have blown away my own definition of CubeSat. I'll just recreate it. Maybe that will run. That. I've got a bunch of stuff I haven't brought across. So I'll just go back to here, back into the Lightbook, and paste it all back in. Now I can, the whole point of this is to be able to remove the clone and copy derives and do it ourselves. Oh, we've got multiple definitions now. You can see that the compiler is being pretty helpful. We can click around and go directly to the problem. We duplicated our definition. Oh, and now I've changed the name of it in my own code versus where the book was. So I'm just going to change that. And again, down in the literal form to recreate a copy. Oh gosh. Hey, so we're hitting nearly the top of the hour, and we've been able to discuss a couple of ways to get through lifetime issues. Oh, this is a bit silly. We'll just blow that away for now. Status message thing turns up later in the chapter. Sadly, we weren't able to implement functional satellites. I'd love to see a whole bunch of little Rustum action lights. No, that's not going to work either. So feel free to ask any other questions. I really encourage you to engage either with the Livebook, so you're able to select any text that you'd like and either highlight, bookmark, or add a discussion. Please don't flame me too badly. There is a human behind this text. And just say something like, why do you write in this way? You know, stuff like that is going to be less useful to me. What else do we have to cover? One thing that I would like to touch upon is that there is another strategy, and we can wrap our types in other types that behave nicely with this the ownership system. RC stands for reference counter, and we're able to opt into reference counting at runtime, if that's useful for your program. Now, this imposes runtime cost, but it gets us a little bit of flexibility. reference counting is also the system that is implemented in most dynamic languages. And so if you've already used JavaScript or Python or Ruby or Perl or any other language, almost, you would have already encountered reference counting. Otherwise, though, I will leave it there. And I really encourage you to play around with the book, play around with Rust. It's a really significant software engineering achievement, and I think you'll learn a lot irrespective of whichever programming heritage you come from. I am just going to change off here and change one thing. This is a really good couple of questions that are coming up. I'm more than happy to answer them. I'll just be 1 second. Okay, so when should we use string and when should we use stir? So stir is more lightweight. It is a reference to some unknown length of bytes. I would say that stick with stir for as long as you can. If you hit roadblocks, create a string. You should try to accept a reference to stir in your own functions, because that will enable people that have their own stirs or strings, or actually there are a few other string types as well, to be able to interoperate with your functions. Right, so that's a really useful point. So Playguru85 has said, like, we introduced this term called a slice. So a slice, at least in the Rust world, is a pointer to some array of bytes. Ignore the term array for now. A slice is an array that the compiler doesn't know the size of at compile time. That's not to say that it doesn't have a fixed length. It's just that the compiler is not able to know that length when it is creating the machine code. And so we talk about a slice of bytes because you can take a reference into, for example, a string, but at like the 10th element of that a string. And so the term of slice is just slightly more flexible. I read that user-defined data structures such as structs and enums should own their data and therefore use strings in that case. Right. So one of the things that I avoided in this demo was introducing lifetime parameters into structures. I think that when you're beginning with Rust, actually creating a string rather than a reference to a stir inside a struct is a really sensible move, because it will avoid a lot of ownership issues. So McNamara has a really good point there. If you have the opportunity to take ownership of data that lives originally outside, that's going to get you a long way while you're learning. You will sacrifice milliseconds of performance, and like it is in single-digit milliseconds, during the object's creation, but and potentially, nanoseconds of performance lost as you're dereferencing pointers. But really, when you're learning a new programming language, you should definitely be okay with that. Don't worry about adopting this mentality that the Rust world seems to take on, which is allocations are evil. they certainly are not. If you're writing so the Rust community attracts people that really care about performance, and they really don't want to sacrifice performance that they don't need to. But those kinds of people that have been programming in Rust, like since it was created, or they've been programming in C++ for 2 decades but have moved to Rust, those are not the kinds of people that are learning Rust. If you already have an intuitive understanding of the memory model or computer architecture, by all means, add references to things and add lifetime parameters and so forth. But right now, you are it's not necessary. Hey, well, it sounds like that's a no. Am I going to do this again? Oh, okay. Actually, I'm just going to pump my own channel. I really would love anyone who wants to hang out to pop over to Twitch TV Tim Clicks. And yahoo! I love that people loved it. I'll have the technology much more in place, and there won't be 5 minutes of mucking around to get things going. If you want to hang out as well, I'm all over socials. Here are some more social links. In fact, I think if you scroll down in the window right now, there are a bunch of author links. And there are some other really, really cool links. For example, I think on this 26th, Chris Matterman is going to be chatting about TensorFlow. So I'm going to be in your place. And this has been a really fascinating a really fascinating hour for me. I've really enjoyed answering people's questions. I'd love to do it again. So with that, I'll wrap up. And thanks again for hanging out.